You know that feeling you get to the end of a super long article and you've completely forgotten a key detail from the first paragraph? Well, it turns out AI models have the exact same problem, just on a massive scale. I mean, how can they possibly remember chapter one of a book when they're trying to write the last sentence? It's one of the biggest puzzles in AI right now, and a new idea called SESA might just have the answer. So let's dive in and break it down.
Yeah, exactly this. Think about an AI trying to sift through a huge legal document or a massive code base. If it can't connect a definition on page 2 with a reference on page, I don't know, 900, it's pretty much useless, right? This isn't just a problem for writing stories. It's the fundamental challenge of what we call long context memory. And that's exactly what we're going to explore.
Okay, so here's our game plan for this explainer. First, we'll dig into this long memory problem. Then, we'll look at how the famous transformer architecture tries to solve it. And after that, we'll check out a totally different approach called Mamba. Finally, we'll see how this new model, SESA, combines these ideas and why it might just be a real game changer. All right, let's get into it. The long memory problem. At its core, this whole thing is really just about connecting the dots. For an AI to truly get a handle on anything complex, it has to be able to link ideas that are super, super far apart. I mean, think about it, right? It could be a tiny clue in a mystery novel's first chapter that only clicks in the final reveal. Or maybe a single function defined in a massive program that gets called thousands of lines later. You even see this in biology, a gene sequence in our DNA that influences another one millions of base pairs away. The challenge is always the same. How do you bridge those massive gaps? So for the last few years, the go-to solution to this problem has been the transformer architecture. You've heard of it. It's what powers models like GPT-4, and it uses a really, really direct method to link information together. Transformers use something called one-hop routing. Now, imagine this. For every new word the model is looking at, it can instantly look back at every single word that came before it, all at the same time. It's kind of like having a book wide open where you can just instantly find any fact on any page. It's one single, direct jump from the past to the present to grab exactly what it needs. And this diagram right here shows it perfectly. Just look at that top path, the one labeled transformer. To get information from a past point, let's call it the start, all the way to the current point, the end, it makes one direct link. That's it. One path, one hop. Super powerful, super direct, but, and this is a big but, it comes with a major catch. And that critical weakness is called dilution. Okay, think of it like this. If you're in a small room with 5 people, trying to listen to just one of them, easy. But what if you're in a stadium with 50,000 people and they're all talking at once? Your attention is spread incredibly thin, right? Well, that's exactly what happens to a transformer. As the amount of information, the context grows, its attention just gets watered down across more and more words. That quiet but crucial detail from chapter 1 gets totally lost in the noise of the entire book. So to try and get around this dilution problem, a whole different family of models popped up. We call them state space models, and a famous one is called Mamba. They took a completely different approach. Instead of a direct lookup, they pass information along, step by step. This is what's called multi-hop routing, and it works like a feedback loop. Instead of looking at everything all at once, information gets compressed into this tiny summary, or a state. You can think of this state as the model's short-term memory. So at every step, it reads the next word, updates its little memory, and then passes that new summary to the next step. It is exactly like a game of telephone, where a message gets passed down a long line, one person at a time. Okay, let's go back to our diagram. Now focus on that middle path, the one labeled Mamba. See how to get information from the start to the end, it has to travel along that single chain. It's hopping through every single point in between. This is exactly what we mean by one path, many hops. It's a clever way to avoid that attention dilution problem, but you can probably guess from our telephone analogy, it creates a whole new issue. And yep, that new problem is exponential forgetting. Let's stick with that game of telephone. What always happens to the message by the time it gets to the last person? It's completely garbled, right? Each time the message is whispered, tiny little errors creep in, and they just add up. Well, the same thing happens here. With every single hop, the memory can degrade just a little bit, and over thousands or even millions of steps, that original information can basically just fade into nothing. Okay, so this brings us to SESA. The designers of SESA looked at the direct access of transformers and the chained feedback of Mamba, and they asked a really brilliant question. What if you could combine the strengths of both?
What if you could have that targeted access of attention, but have it inside a robust, stateful feedback system? What if you didn't have to choose between dilution and forgetting? And here is SESA's brilliant solution, right there at the bottom of our diagram. It's not one direct path like a transformer, and it's not one single chain like Mamba. Look closely. SESA creates many different paths for information to travel from the start to the end. It's like a whole network of routes. Some are short, some are long. This is the key idea right here. Many paths, multi-hop. So how does it actually create all these paths? Well, the magic is in this component called the SESA mixer. Think of it like a really smart switchboard operator sitting inside the feedback loop. At every step, instead of just passing the memory from the one step right before it, this operator uses attention to look back at the memory from all the previous steps. It then intelligently mixes and combines them into a new, richer memory to pass forward. See? It's not just passing a message, it's constantly remixing the entire history of messages. It's using attention on memory itself. And the result of this pretty incredible architectural change is a huge theoretical advantage in how the model remembers things over time. This chart really gets to the heart of it. On one side, you've got transformers, where memory dilutes really fast, or Mamba, where it can forget exponentially. But then you look at SESA. Its memory decay is much, much slower. It follows what's called a power law, which is a fancy way of saying the influence of past information just fades away far more gracefully over those long distances. And the reason it can do this is that many paths, multi-hop system we just saw. By constantly reintegrating and pulling together information from all these countless different routes through its past states, it creates a much more robust, a much more resilient memory. It's not putting all its eggs in one basket, either a single direct read or a single feedback chain. It basically mitigates both of the big failure modes we just talked about. So, to wrap all this up, the key takeaway here isn't just about some shiny new model, it's really about a new way of thinking about how information flows through time in these AI systems. So let's just recap it one last time. A transformer gives you one path and one hop. That's your direct read. Mamba gives you one path, but many hops. That's the sequential feedback chain. And SESA? SESA gives you the best of both worlds. Many paths and multi-hop routing, all by cleverly sticking an attention mechanism right inside that feedback loop. This, right here, is the crucial difference in how these models route information from the past to the present. And this brings us to a final, pretty provocative thought. Memory is just fundamental to intelligence, right? So if we are fundamentally changing the mechanism for how an AI remembers, moving from a simple lookup or a fragile chain to this rich, multipath system, what other aspects of artificial thinking might this unlock? It really suggests that the architecture of memory, that could be the key to the future of how these models learn, reason, and ultimately understand our world.